today I'll be explaining about disjoint set union, or what is also called union find. So what is this concept? What is disjoint set union or union find? So we start with two separate sets of nodes, and we would want to join or unite these sets of nodes or components by picking a node from each set. So we pick node 3 and we pick node A, and then we would unite these two sets of nodes into one set. So how would we be able to do this? So let's start with an example. In this, I will be using set and component interchangeably. So this is a set, and it is also called a component, and which is the same for this one. This is also called a component. So let's say this this node is the parent node of this set, which means it is the representative node, and this is the representative node of this set. So if we want to unite, if we want to join these two sets, then we would need to pick a node from each set or each component. So here we pick node 3 from this set and node 8 from this set. And the next step, so after picking these, the next step is that we would find the parent of each picked node. So the parent of node 3 is obviously this one, node 1, and the parent of node A is node 2, and we find the parent of A by recursively finding the parent. So we go to the parent of A, the contiguous parent of A, that is 9, and then from 9 we go up here to find the parent of 9, which is also the parent of A. So now we've got the parents or the representative nodes of these two sets. We can then use these two parents to unite or join these two sets by setting the parent of the smaller set, because this one only has 3 nodes and this one has 4 nodes. So this one is obviously a smaller set. So we would want to set the parent of the smaller set as the child of the parent of the larger set. So this is the child of this, and so we would have this one. So this is the child of the parent of the larger set. And so now we have joined these two sets or merge. Yep. And the related LeetCode problem, this one is actually a very hard problem, and it's not it is kind of intuitive, but it's still hard for you guys if you're not really familiar with union find, or this is the first time you encounter this concept and a related problem. But we will walk through this very slow. I promise you it won't be overwhelming, but it's okay if you feel a little bit overwhelmed, because it's basically a hard problem. Yeah, the name tells the whole story. So this problem is called the greatest common divisor traversal. You can have a read at this question by pausing the video. So if you have had a read of the problem, you will know that this one we essentially return true if for all pairs I and j, given that I is on the left of j, there is a sequence of valid traversals for each pair. And by that, I mean, so what is called a sequence of valid traversals? A sequence of valid traversals essentially contains, all traversals where each is a valid traversal, and that valid traversal is a traversal from a number to another number, only if those two numbers share the same common divisor, or what we say here is the greatest common divisor, and the greatest common divisor must be greater than 1. Also in this, I will be using factor, not divisor, because I think factor is reasonably more intuitive than divisor. So if the two numbers, let's say 4 and 12, if they share the greatest common factor greater than 1, then we can traverse from 4 to 12 and vice versa. And we don't really care about the greatest common factor, because if we are able to identify a common factor that is already greater than 1, then that means that the two numbers belong to a valid traversal already, right? Because let's say a common factor between these is 2. When 2 is a common factor, we already know that it is already greater than 1. What if 2 is not the greatest common factor? Well, it doesn't matter, because if any common factor is already greater than 1, then the greatest common factor must be greater than that number, greater than 2, and which means it already satisfies the greater than 1 condition. So our solution is we will go through each number and we will find the the prime factors of that number, or we will map the prime factors of that number to the index of that number. Well, why won't we put the number here? Because there might be duplicates in the array, so it's safer to use the index, as it's like a unique indicator of each number. So when we come to the first number, we see that this is number 4. It's at index 0, and it has the prime factor 2, because 4 is 2 times 2, right? Then we will add to the table. So this is a hash map, by the way. This is a hash map, and the factor 2 maps to the index of the first number, that is 0. So we know that the number of the number at index 0 has the factor of 2, and this is a prime factor. And also these are the components. So these are the components of the union find that you saw earlier, and then we will merge these together. If say 0 can traverse to 1, then we will merge these together. We'll merge these sets or components together. And these are actually the indices, because as I have discussed earlier, we only use the indices of the numbers in the array, not the actual numbers themselves, because there might be duplicates. So we want to uniquely define them. Okay. So the next number is number 3. And now we find the prime factors of number 3. Well, it only has one prime factor, which is also itself, that is 3. And then we will map that factor to the index of the number that has this factor, that is 1, because 3 is at index 1. And for the next number, that is 12, we can see that 12 has the factors 2 and 3. Because this is the prime factorization of 12. Well, if you don't know what prime factorization is, it's essentially a it's like a representation where we represent a number as the product of only prime numbers. So 2 is a prime number, and 3 is a prime number, and 12 is represented by this one. So 2 times 2 times 3. 2 has 2 as a factor. And we also see that previously we already had a number at index 0 that has the same factor 2. That means we can traverse from that number at index 0 to the number 12 here, right? Because they share the common factor, that is 2. And 2 is actually greater than 1, so it satisfies the condition stated in the problem. And so because we can traverse from the index, the number at index 0 to 12, then and 12 is at index 2, then we need to join the two indices of those two corresponding numbers, and those are 0 and 2. So from index 0 we can go to index 2, because the number at index 0 is 4, number at index 2 is 12, and 4 can traverse to 12 and vice versa, using the common factor 2 here. We also see that 12 has a prime factor 3. Well, that means we can traverse from the previously seen number at index 0 that also has a factor of 3 to this number 12 here, and that indicates that we need to join the number 12 or the index 2, which represents 12. We need to join the index 2 with index 1, because those are the indices of the numbers 12 and 3 that share the same common factor 3, right? So we need to join the indices 2 and 1. So that's why we have this 2 and 1. So we join the first component, that is 0 and 2, with the second component, that is 1, using this. Yes. So the last number, that is 8, we do the prime factorization of 8. That is 2 times 2 times 2. So 8 only has one factor, that is 2. We only saw a number that has a factor of 2. That is the number at index 0. So that means we can traverse from the number at index 0 to number 8, right? And number 8 is at index 3. So that's why we need to join the number at index 0 and the number at index 3. So 0 to 3. And now if we look at our the components here, we can see that all components have been joined into only one component. And because it's only one component, then it essentially means that now we can traverse from any node to any other node in this component, or we can traverse from any number to another number, and we can actually verify this. For example, if I want to go from 1 to 3, that means from 3 to 8, then a sequence of valid traversals is from index 1 to 2, and then 2 to 0, and then from 0 to 3. So from 1 to 2, right? Because if we see like if I is 3 and then j is 8, then we cannot directly traverse from 3 to 8, right? Because they share no common factor. And so we can do like a valid sequence of traversals by first going to 12, which means from index 1 to index 2, because these two share the common factor 3. So we can traverse from 3 to 12. And then from 12, we go to 4. So from here, we go to 0, from 12 to 4, and then from 4 to 8, which is a sequence of valid traversals. And actually, we can go from here to here because both 12 and 8 share the same common factor 2. But going from 12 to 4 and then from 4 to 8 is also a valid one, and that's essentially what we need. We don't really need to identify like the shortest path or something. We only need to define if a number can reach another number by traversing through a sequence of nodes or not, or numbers or not, and that is the case. Now let's go to the code. This is the code. It starts with the union find class. This is the class that implements every union operation, or joining operations, joining the components. So we will represent the relationships using this parent array, and the size is also an array where each element represents the number of nodes, or the number of numbers that belong to that component. And count is the number of components, so we keep track of this, and at the end, if the count is exactly 1, then we will return true. So this constructor first it initializes the parent as an array of n elements, and also size is an array of n elements. The count, we start with n elements, so n is the length of the given nums array, or the number of numbers in the input. So the count is essentially is initially that number, because we start with all n components, right? Because initially we have no joined components yet, so all of them are separate. And from 0 to n, this is a little bit tricky here, because the nodes are not represented by the numbers themselves in the nums array, but they are represented by the indices. And what this tells us is that the parent of I is I, which means we are assigning each node, or each number, or each index, you may say, we are assigning each number to itself. Initially, parents is actually 0, 1, 2, because this is index 0, this is index 1, and this is index 2. And what this tells us is that the parents at index 0 is also 0. That means we are mapping a number into itself. So 0 is the parent of 0, and 1 is the parent of 1, which is the same with 2. So 2 is the parent of 2. Yeah, because we initially don't really have like any other parents, any other parent of each node, right? Because each node is represented as let's say if we have like if n is equal to 3, then we would have component 0, component 1, and component 2. And so 0 is the parent of itself, 1 is the parent of itself, which is the same with 2. So that's why we have this. As we go, we will update this parents array. 1, this may be 2, this may be 0, and this means the parent of 0 is 1, parent of 1 is 2. We can represent in like the graph like this. So 0 is the child of 1, and then 1 is also the child of 2. So this is this is the case. Well, and so this is the parent. This is the parent of this one, and this is the parent of this one. And then size, we start by assigning the size of 1 to each index, because as I said earlier, the size is only itself. So this is size 1 because it's initially we have 0, 1, and 2, right? And so this has the size 1 because this is a component itself. And this is also a component itself, so it has the size 1. And this is also a component itself, it has the size 1. Later, if 0 joins with 1, then this is a component with size 2. And 2 has a size 1 as before. So this is the find method, and what it essentially does is that it finds the parent of an index, or of a number. Yeah. And so because you have seen the find operation before, right? So let's say so this is essentially that one. Yep. So this is this one. Yeah, this is what the find operation does. So it recursively finds the parent of the selected node. Yeah. So if x, so here we have node x, and so x is this node right here, and it will it will find the parent of x by recursively going up and up and up to the parent. Yep. So the logic here is that if the parent of x is not x, then it will go find the parent of x. So what does this mean? It means that if a node is not a parent of itself, then there must be another node that is its parent, right? So what we do is that we go and find the parent of it. And when we find up to the point, so up to the point where we reach 2 here, that means the parent of 2 is 2, then we would return parent, we would return that parent, which is x. So this is the case where parent x is equal to x. Then we would return that parent. We would return x, and then that will be assigned to the parent of x, and then will be returned. So it's like on the way back in like the reverse sequence, because I mean you're already familiar with like recursion logic, so this shouldn't be too difficult for you guys, I guess. So yeah, it will return so it will return 2 to 9, and then from 9 it will also return 2 to 8. So that's why we know that 2 is the parent of 8. Yeah. And then we come to the union function. So this is the main function. So what it does is that from the two given nodes, node x and node y, which is the same as node 3 and node 8 here. So in the two nodes, from the two nodes, we will find the parent of each node. Just like here, we will find the parent of 3 and the parent of 8. So px is the parent of x and py is the parent of y, which are found by running through this find function here. So we'll find the parent of x, which is px, and then find the parent of y, which is py. If the two parents are the same, which means that the x and y belong to the same component, right? X and y belong to the same component. So let's say we select 3 and 5, and then we discover that they share the same parent. That means they must be in the same component. And so we just return in that case, because we don't need to unite, or we don't need to merge or join anything, because they are already in the same component already. So we don't need to join anymore. But if they are not equal, that means that they belong to two separate components. And then we must merge the two components, and we union by size. Well, that means if the size of the component that has px as its representative, if the size of that component is smaller than the size of the other component, the component that has py as its parent is the larger component, right? So it will be the parent of the smaller component. Yeah, so py is the parent of px. So that's why we said parent of px is py. Yeah, and then we would increase the size of the component that has py as its representative. We'll increase that exactly by the size of the other component, because we're merging them, right? So we're just adding all the nodes from the smaller component to the larger component. And else, this is the other case. So if the component with px is greater than the component with py, then what we would do is that we would set the component with px to be the parent of the component of py, and then px, the size of the component with px is incremented by we're just adding all the nodes from the other like smaller component to the larger component, and then we would decrement the count by 1, because we're merging, right? We're essentially so we were merging. So at first we got like two separate components, right? But after the union operation, we have merged them into one component. So we must decrement the count by 1, because the number of components has decreased by 1, which is the same as this. So let's say we start with 0, and then 1, and then 2, right? So the count is initially 3, because we got 3 components, 0, 1, and 2. But after merging 0 and 1, this has now become one component, and this is the second component. So count must be decremented by 1, which is 2. So count now is 2. Yeah, and then so that is essentially the union find class. And now we are going to the solution. So we start with so n is that is the number of numbers in the given array, and we initialize a new union find object called UF here with n objects. Sorry, with n components, and then this is our factor index hash map. So that is the hash. That is the number here that we saw earlier. Factor maps to index. Yeah, so this is the dictionary factor index with factor as the key and index as the value. So we will go through each number in the nums array. Yeah, we will call it num. So each nums I we'll call it num. And we start with f equals 2, which means we start with the factor 2, right? Because because the smallest factor we can start with is 2, because we don't want to start at 1, because it makes no sense to start at 1, since we need to find a common factor that is greater than 1 for the sequence of traversals to be valid. All right. So why do we have this condition here? F times f that is smaller than or equal to num. Well, if you think about it, well, our goal is to find the prime factors, right? Is to find the prime factors of every number, and for every num, we need to find a all the prime factors f, and we can check if f is a prime factor of num by by dividing num by all the numbers from 2 up to the square root of num. And I won't explain this in detail because the video is fairly long already. So you might need to if you're not familiar with this, then you might need a couple of or maybe just one video on the internet to know why this is the reason. But whenever we need to check so we check f from 2 to nums. So f goes from 2 to nums. And if this is a if num is divisible by any f from 2 up to the square root of nums, then f is a prime factor of num. And this is why we gotta check. So this is actually f squared smaller than or equal to num, because so we see that we need to check for all f, given that f is smaller than or equal to the square root of num, right? Because so f goes from 2 to num, and here we start with f equals 2, which is what we want. So from 2, it goes to the square root of num, right? That is the range of f. So f goes from 2 to square root of num, and if we square everything up, we will get, so this is f squared smaller than or equal to num, right? So that's why we have f times f here, which means so f with f squared is f times f, smaller than or equal to num. Yep, that is the same. So as long as f is a potential prime factor of num, then we will do this. We will check if num is divisible by f. That means it has 0 as the remainder. So if num is divisible by f, that means f is a factor of num, or the current num. Nums I. And when we know that f is a prime factor, is a factor of current num, or you can say the prime factor of the current num, then we check if f is also a factor of a previously seen number, which is the same as here. So when we go to 12, we check, we see the prime factor 2, right? So f is equal to 2, and then we check if we have previously seen a number with the same factor 2, and that is the number at index 0. So we will map 2 to 0, or we will join 2 to 0. So that is the logic here. So if that factor f already exists in the factor index dictionary, that means that there was already a number that had this factor f. And so f is the common factor among that previously seen number and this current num here. That's why we gotta unite num with that previously seen number, and this num is represented by its index, as we have discussed, so we unite the index of num with the index of the number that has f as its factor in the dictionary. Or else, which means if we have not seen that factor f before, then this is the first time we see a number with the factor f, just like this. Just like when we got into 3, we see that 3 is the first, like the factor 3 here is the first time that we have ever seen the factor 3. And so we just simply add it to the hash map. And it maps with the index of the number that has 3 as the factor, right? So first time encountering the factor t, we just map that factor f to the current num, or the index of the current num to be precise. Yeah. And then, well, this is the logic that is worth mentioning about, because this means so we remove the repeated factor to move on to the next prime factor. Oh, I haven't talked about this, but this is fairly important as well in terms of runtime and efficiency. So we'll discuss this. So when num is divisible by f, when num is divisible by f, what does it tell us? So let's say if there are two numbers, right? If there are two numbers, 8 and 16. So yeah, so these two numbers, they have a lot of factors in common. They have a lot of common factors. They have 2 as a common factor, they have 4, and they have 8 as a common factor. But if we think about it, do we need to account for these cases? Do we need to check if 4 and 8 are the common factors of 8 and 16? For me, we don't. Why? Because first of all, we go from 2, right? We go from f equals 2 on the way up to from 2 and on the way up. So obviously we encounter 2 first. So we map 2 to the index that represents a. So let's say that's I8 here. And then when we go to 16 and we see that there is so 16 also has 2 as a prime factor, and we see that previously there was a number with the prime factor 2 as well. So we will map we will join 16 with 8, and that is what we essentially do. And we don't really need to check the cases 4 and 8. Why? Because at the end of the day, our goal is only to check if 8 can join 16 or not, right? That's the only thing that matters. When we got to f equals 2, we have already done that, right? We have already done the work, checking if 8 belongs to 16 or 16 belongs to 8, belongs to means that the two numbers can traverse through each other. So that's so that's the logic, and that's the only thing that needs to be done. And so when we have finished that, using 2 as the bridge, using f equals 2 as the bridge, then we don't need 4 and 8 anymore, right? We don't need f equals 4 anymore, because why? Why would we need to check f equals 4, right? Because it doesn't mean anything. I mean, if we check it, we would end up having 4 maps to 8, and then when we reach 16, we will see that 16 has a factor 4, and then 8 also has a factor 4. Then that would mean we join 16 with 8, right? But we have already done that, right? We have already done that when f equals to 2. So when f reaches 4, we're going to do that again. Well, it's kind of a little bit redundant, right? So we need to remove these cases. If you notice, you will see that 4 is actually just 2 times 2, and 8 is actually just 2 times 2 times 2. So that's why we need to divide num by f as many times as needed, because we only check for the prime number cases, right? We only need to check when f is equal to 2, then to 3, to 5, and then to 7, because and etc., because these are the prime factors, right? Only the prime factors matter, right? Because 4 is just 2 times 2, and with this we can just take 2 already, right? Why would we need to take 4? Why would we need to take 8 when we can just take 2, right? So that's why we gotta divide num by f as many times as needed to remove all of these numbers, all of the 4, all of the 8, and so on. But dividing by this does not remove 3 and does not remove 5. Why? Because 3 and 5, well, it's just like, so if we divide by too many times, then we would remove this, and then remove this, and this, which will remove these numbers. We can't remove 3 because 3 is essentially just 3, right? If num has 3 in its product, then when we divide by 2, we won't divide by 3. I mean that's kind of straightforward, right? And we only do that if num is divisible by f. Well, what this indicates us is that it tells us that the factor f, let's say f equals 2, f equals 2, that it still exists in num, okay? So if num equals 16, then we divide by 2, we get 8. So 8 is still divisible by the factor 2. That means that 2 is still in 8. So we need to divide by 2 again, and then we get 4, and we need to divide by 2 again, and we get 2, and then we need to divide by 2 again, which will give us 1. And then from this 1, we so from this 1, where it contains no f equals 2, and so this while loop breaks. Because we have, it indicates that we have just removed all the factors 2 of this num already. So we can move on. But let's take another example that is better than that one. Let's take maybe 12, right? Yeah, maybe 12. So it's 2 times 2 times 3. This is the prime factorization of 12. And so with 12, when we see that 12 is divisible by what? By 2, right? Divisible by the factor 2. So that means there are still instances of 2 in the product of 12. That means we need to divide 12 by 2, which will give us 6. And then from 6, we check, well, this is still valid because this is still valid. That means so after removing 2, we essentially just removed this, right? And now we got 2 times 3, that is 6. And so we would check if 6 is divisible by 2 or not. It is, right? So we need to remove 2 from 6, which will give us 3. And that is this one. We remove 2 from the representation, from the prime factorization of 12. And now we're only left with 3, right? So this is the case. So when now we check it, 3 is 3 divisible by 2? Obviously, it is not, right? It's not divisible by 3. And so we can move on to the next prime number. And so that is essentially the logic that is. And from this, if you noticed, because 12 is, it is 2 times 2, right? So it has 4 as its factor. We're not talking about prime factor. We were talking about factor, okay? 4 is a factor of 12, right? But after removing all of these, when f is equal to 2 already, then it automatically eliminated the case where f is equal to 4. And this is very efficient because 4 is obviously not a prime factor, right? And our goal is just to loop through the prime factors. We need to check f equals 2, equals 3, and then equals 5. So we skip through 4. Yeah. And the logic applies for everything else. So if we got like 3, 9, then when we go to f equals 3, then f equals 3, then we would remove all of these. So remove all the 3 and 9. Because 9 is not a prime factor, it's just 3 times 3, right? So we remove all the prime factors of 3. We will remove only instances of 3 in the prime factorization of that number to move on to the next prime factor, that is 5. Oof, that's a bit wordy, but it is worth noticing if you want to dive deep into this. After removing all the instances of the prime factor, let's say f equals 2, then we would increment f. So we would move on to the next prime factor, just a factor. So when we increment 2 to 3, then we will go through the loop again and check for all the we would do everything again. We would need to check if the prime factor 3 already exists in the factor index dictionary or not. If it exists already, then there was a number with the prime factor 3, and then we need to unite the current num with that number that shared the common factor 3, and then we remove all the instances of the prime factor 3 so that we won't have to loop through the cases where f equals 9 or equals 27. That is 3 times 3 times 3. Yeah, and then we move on to the next factor, and so now f is equal to 4, right? And then and then here we so when f is equal to 4, then this will not be executed because even though even though originally num was 12, right, and 12 is divisible by 4, but now it is not valid anymore because look at this. Now, because we have previously removed all the instances of 2 from 12, right? We've got, so at the start we've got 2 times 2 times 3, right? But after when f is equal to 2, we already removed all the 2's here, right? So now num is actually just 3, right? Num is actually just 3. So when we go to 4, we cannot find anything else. Even though 4 is a factor of 12, but we cannot find any we cannot check that num is divisible by f, because num is at the moment num is 3. It was originally 12, but now it is 3, which already removed the 4 from num. So yeah, we won't loop through 4 anymore. And now, so this is the case. This is so the case where num is the factor that appears only once in its original prime factorization. So what do I mean by this? It means that, let's say if yeah, so let's take 12 as our example again. So yeah, so here when so after f equals 2, right? After f equals 2, we've removed everything else, and now num is actually 3, right? And when num is 3, then it would mean that we won't go through this iteration again, because with this condition, it says that with this condition, it is f squared, right? F squared is more than or equal to num, right? And num is 3, and f. So now we go to the prime factor f equals 3. So 3 to the power of 2 smaller than 3. No, this is wrong, right? This is wrong. So this iteration won't be executed, which means that we didn't assess the case where f equals 3, right? And why is that the case? Because we said earlier that we only check the prime factors up to the square root of num, right? Up to the square root of num. So obviously, when f is equal to 3 and is equal to num, obviously this does not satisfy the condition. So we do not do that. And this only happens when we only have one instance of that factor. So we only have one instance of 3 in the prime factorization of 12. Because we cannot check the case where f is equal to 3, which means that we might miss these logics. We might miss if there was a number that had 3 as its factor. So that's why we got to account for it, right? We got to account for the case where num is a factor but still greater than 1. Then we got to account by that by checking if that factor is already in the dictionary or not, because it specifies that num is also a factor of the previously seen number, right? So now we treat num as a factor, just like f here. So if num here and num is also f in this case, if num or f was already a factor of another number that we previously saw, then we would need to merge the two numbers, right? We need to merge the two components of those two numbers, the two components that contain the two numbers, which means the current number and also the number that has num as its factor. Yeah, but if this is the first time we see the prime factor num, then we would need to map it to the index of the current number, which is the index of 12. So yeah, then in the end, we return the count of union find, which means, as I said earlier, that is the number of components. So eventually, if there is only one united component left, which means that everything, like every node, is merged to like the largest component, and so we can say that all pairs ij can be traversed, because if all the numbers are merged into one component, then obviously we can traverse from any node or any number to another number, and so that is the only case where we will return true. The final one, so this is so we can traverse from all the nodes. So this is where the case where count is equal to 1, because these nodes belong to these nodes belong to the same component, right? We can traverse from 3 to 2 by taking this path, can traverse from 4 to 0 by taking this path, and from any node to any other node in that. So count is equal to 1. So all pairs ij can be traversed. So this is true. But for the case where, let's say, this is 0 and this is 3, this is 2 and this is 4, right? So we can traverse from 0 to 3, but we cannot traverse from 2 to 4. So this is the case where count is equal to 2. And this is actually not the valid case, right? This is false, because let's say if I is 2, and j is 3, then it is not valid because I need to traverse from I to j, right? Because let's say I is on the left of j, and we need to traverse from I to j, but we cannot do that. We can, yeah, we can. It's impossible to do that because I can only traverse to 4, right? And from 4 we cannot jump to 3. We cannot jump to 3 from 2. So it's impossible to traverse from I to j. That's why this breaks the requirement of the problem. So we return false. We need to run the code to check if it was a valid solution. Oh, I think we can do that. Yeah, we can run that again. Yep. So that was accepted as a valid solution. So that confirms that our code is correct. So I hope that was not overwhelming for you guys, and I hope you have enjoyed it and found this video helpful and enthralling, and hope that it has helped you a lot in comprehending this sophisticated concept. And yeah, as always, happy leet coding.